So today we're going to look at adding and subtracting radicals, making sure that everybody knows a radical is this red symbol, which we used to know as a square root. Now we know that the number here, the index n, can be 2 for square root, 3 for cube root, and so on. And so let's sort of use those ideas to see if we can add these together like numbers, because really these are just numbers, okay? They're irrational numbers. So I've got these two numbers here, and root 50, square root 50, and 3 root 2, 3 square root 2. And they don't look like they can be combined because they're not like radicals. And if you're not sure what like radicals are, check out the video, I've linked it down below. So they don't appear to be like, but these are the unsuspecting like radicals. So if we notice here, 50 can be written as 25 times 2. And so it's important for you to sort of establish an understanding of what your perfect squares are and your perfect cubes. Know the first 12 perfect squares and know the first 5 perfect cubes. So 50 is 25 times 2, right? And notice I magically decided 25 because 25, the square root of 25 is 5, and I can do that in my mind. There's nothing to do here. That just stays as 3 root 2. The idea here is to bring as much number outside the radical as possible to write them in the most simple way. And there's nothing I can do with 2. 2 is simple. Now here, I can actually split that in 2, like splitting the atom. So I can say the square root of 25 times the square root of 2. That's a math rule. It's a math property for radicals, and it's true. And that's plus 3 root 2. And now I can just take the square root of 25. So the square root of 25 is 5. And remember, these are all glued together by time. So 5 root 2 plus 3 root 2. And now these radicals are like, because the number under the radical is the same, and so are the indices. This is the square root, this is the square root. I can't combine a square root with a cube root, okay? And so that allows me to then add the coefficients. So 5 plus 3 is 8, and 8 root 2. And there's the final answer, okay? Now let's take a look at another one here. These are all square roots. And the numbers under the radicals don't look alike. They don't look like radicals, but these are unsuspectingly like. So let's take a look here. So looking at 27, I think a little bit and think, what's the biggest perfect square that goes into 27? And it's 9. So 9 times 3 is 27. And then come to here. There's not much I can do with a 5. You see, 5 is prime. I can't break it down. And go to 80. Does anybody know what the biggest perfect square is that goes into 80? The answer is 16. Yeah. So the square root of 16 times 5. And you can use your calculator usually on tests just to trial some numbers. Eventually you're going to get the right number, okay? And the same here, even though there's a number out front, the 12 can be broken down. 4 times 3 is 12. There's the number. So minus 2 square root 4 times 3. All right, now we're in good shape. Now we can split these atoms. So split it up here, split it up here, split it up there. You might do these a little differently. That's okay. And so minus the square root of 9 is 3. So I'm just going to jump right to the answer. And notice that 3 is stuck inside the radical jail. It can't escape. So 3 root 3. 3 root 3 is the same as root 27, because 3 squared is 9, and 9 times 3 is 27. This one I can't do much with. That's 3 root 5. This one here, I'm splitting the atom. So let's see. What's the square root of 16? The answer is 4. I know you know that. And then what's the square root of 5? Well, how about the square root of 5? So the square root of 5. Okay, 5 isn't a perfect square. So the only other way you could represent it is by putting that into the calculator and getting a decimal approximation. We don't want that, okay? And then minus 2 times the square root of 4, which is also 2. Do you see? So I swap out the root 4 for the regular number 2. Now the 3's inside the radical. There's not much I can do with that. It has to stay. Now I clean it up. Now notice all of a sudden, look, this and that are like radicals because the number under the radical is the same. So I can start combining these. So that's -3 and that's -4. So I'm just going to replace that with a 4. So -3, -4 is -7. And then I can combine these middle two terms, these two middle radicals, by adding the coefficient parts. Since the radicals are the same, I can do that. So that's 3 minus 4, which is -1, or just minus √5. The final answer, even though it looks really strange, especially if you're new to using radicals, that's a number. It's on the number line. I know it's negative because a negative minus another number is negative. So that's clearly to the left of 0 on the number line. And it represents a fine answer. And you leave it just like that. Okay, so that's how we add and subtract radicals, and making sure that all of the radicals are like first, and then you just combine them, making sure that the radicals are equivalent, and you combine those coefficients. If this is helpful, please slap a like on the video and subscribe for more videos to come.